Welcome back. This is Mrs. Rubright with Algebra 1 Honors. Today's lesson is 9.3, Exponential Growth and Decay. Alright, so we're going to be describing the end behavior of the growth function. This one is saying to use a graphing calculator, which we do not have. So we are not going to be able to do this other than I'm just going to show you what the graph should look like. So this graph should look like something like that. Alright, so what is the end behavior of the function? You describe the function values as x increases or decreases without bound. Using the trace feature, move the cursor to the right along the curve. Describe the end behavior as x increases without bound. So the value of the function increases without bound. So like it increases infinitely, right? Forever. Using the trace feature, move the cursor to the left along the curve and describe the end behavior as x decreases without bound. So the value of the function approaches but never reaches what? What is it going to approach but never reach? The x-axis, so 0. It's going to approach but never reach 0. Describe the domain and the range of the function. So what would be my domain? My domain is my x values. My domain, so your x values. Range is your y values. So in terms of my x values, my domain is what? What x values get covered? All real numbers. It goes on forever in this direction and this direction. So it's going to be opening up forever. It's going to cover every single x value. What about your range? Your y values are greater than 0. It's going to get as close to 0 without ever hitting it, right? All real numbers greater than 0. Identify the y-intercept of the graph of the function. So your y-intercept is at 200 in this one. So looking here, 200, because if I plug in a 0 for x, your y-intercept is when x equals 0. And anything to the 0 power is 1. 1 times 200 is 200. So 0, 200, right? An asymptote of the graph is a line that the graph approaches more and more closely. Identify the asymptote of this graph. Where's my asymptote? Y equals 0, right? Your x-axis is when y equals 0. It's your x-axis, which is y equals 0. Why is the value of the function always greater than 0? Because 0 is an asymptote. It'll always get as close to that as possible without ever touching it. All powers of 1.1 are positive, and 200 times a positive number is positive. All numbers of 1.10, all powers of 1.10 are positive, and 200 times a positive number is positive. Recall that a function in the form of y equals ab to the x represents exponential growth where a is greater than 0 and b is greater than 1. If b is replaced by 1 plus r and x is replaced by t, then the function is the exponential growth model, where which is y equals a to the 1 plus r all raised to the t, where a is the initial amount and the base 1 plus r is the growth factor. R is the growth rate and t is the time interval. The value of the model increases with time. Alex buys a rare trading card for $4. The value of the card increases 40% per year for 4 years. Identify the initial amount and the growth rate. So his initial amount here is how much? $4. And his growth rate? 40%. Write an exponential growth equation for this situation. So his initial amount, and then 1 plus 0.4, 40% as a decimal is 0.4, right? To get out of a percent into a decimal, you move 2 places away from the percent sign and drop the percent sign. To get out of a percent into a decimal, you move 2 places away from the percent sign and drop the percent sign. All right, so this is our equation. We could put 0.4 if that makes you feel better. All right. So if we are going to plug and chug, if we plug in a 0, anything to the 0 power is 1. 1 times 4 is 4. To the first, 1.4 to the first is 1.4, and 1.4 times 4 is 5.6. 1.4 squared times 4 is 7.84. 1.4 to the third times 4 is 10.98. 1.4 to the to the fourth times 4 is 15.37. Graph the points from the table using appropriate scales. Draw a smooth curve connecting the points. Label the axes. All right, so we have our value, right, our money, and our time in years. So we have 1, 2, 3, 4, 5, 6, 7, 8 years. We're going to go by $2, right? $2, $4, $6, 8, 10, 12, 14, 16, 18. Okay. So 0, 4, 1, 5.6, 2, 7.84, 3, 10.98, 4, 15.37. Identify the y-intercept of the graph. What does it represent? So your y-intercept is when x is 0. So it's going to be $4. So it's the price that he bought it at, right? The initial value, or the price he purchased it at. So it's $4. The value of the card when Alex bought it. What is the growth factor 1 plus r written as a percent? 140%, right? The initial value plus the 40% increase. Use the graph to estimate the value of the card in 3.5 years. Then explain why it makes sense to connect the points from the table with a smooth curve when graphing this function. All right, so 3.5 years. Let's look at 3.5 years. 3.5. About $13, right? If I go to 3.5 and I go up and over, it's about $13. It makes sense to talk about the value of the card at any point in the year, and the value doesn't have to be a whole number, right? It can have change. It could be worth $15.50. Like it has all those in-between points. Describe the domain and the range of the function y equals 4 times 1.4 to the t outside the context of this problem. Do all these values make sense in the context of the situation? Why or why not? So your domain would be all real numbers, right? your range would be y values that are greater than 0, right? So in this one, no, it doesn't make sense because the domain is limited to values of 0 to 4 years. So the range is limited to values from $4 to $15.37. Right? It doesn't go on forever. They only care about those 4 years. Describing the end behavior of the decay function. So if we were going to plug this into a graphing calculator, see what it would look like, it would look a little something like this. Okay? Using the trace feature, move the cursor to the right along the curve, and what's going to happen? It's going to get as close to 0 as possible without ever touching it, right? It will approach 0. Using the trace feature, moving to the left along the curve, what's going to happen? It's going to increase without bond, right? It has no boundary. It's just going to keep increasing forever. Forever, forever, ever. Right? It's going to increase exponentially. See how I did that? Increase exponentially. Describe the domain and the range of the function. So your domain, all real numbers. And your range, what's my range? Y values that are greater than 0. Identify the y-intercept of the graph of this function. So my y-intercept, let's look at the equation. They gave us this equation. My y-intercept is when x is 0. Anything to the 0 power is 1. 1 times 500 is 500. Identify an asymptote for this graph. Y equals 0. Y isn't an asymptote because it's going to get as close to that as possible without ever touching it. Recall the function in the form of f of x equals a b to the x represents an exponential decay when a is greater than 0 and 0 is less than b, which is less than 1. If b is replaced by 1 minus r and x is replaced by t, then the function of exponential decay model becomes y equals a times the difference of 1 and r raised to the t power, where a is the initial amount and the base 1 minus r is the decay factor, r is the decay rate, and t is the time interval. Modeling exponential decay. So you pay $12,000 for a car. The value then depreciates at a rate of 15% per year. That is, the car loses 15% of its value each year. Write an exponential decay equation for the situation. All right, so this one's going down 15%. So it's the whole amount, the whole value, 100% minus 15% each year. So minus 0.15, 15% as a decimal. Okay? And what was the initial price? $12,000. Okay, so you paid $12,000 for the car, and it's depreciating by 15% per year. So it's 1 minus 0.15. So it's worth 85% of its value each year. Okay? So, complete the table. Anything to the 0 power is 1. 1 times 12,000 is 12,000. So the first, so we have 1.15 times 12,000. Sorry, why did I say 1.15? Sorry, 0.85, right? 1 minus 0.15 is 0.85 times 12,000. I got $11,730. Did I do something wrong? 1 minus 0.15, I feel like it's messed something up. So that's 0.85 times 12,000. I did. I thought it sounded weird. 10,200. I don't know how I miscalculated that in my calculator, but I did. 10,200. And now let's do this again. 0.85 squared times 12,000, 8,670. 0.85 cubed times 12,000, 7,370. And then I'm going to do the next ones. I get 6,264, 5,324, and 4,526. Then they want you to graph these. Okay, so we need to put our value in money and our time in years. We're going to go with 1, 2, 3, 4, 5, 6, 7 years. And we're going to go by 2,000. So let's go 2,000, 4,000, 6,000, 8,000, 10,000, 12,000, 14,000, 16,000, 18,000. All right. So we know that we bought it for 12 grand. So it starts there. And then at 1 year, it was worth 10.2. At 2 years, it was worth 86. So like 74, 62, 53, 45. All right, identify the y-intercept of the graph. What does it represent? It's $12,000. It's the purchase price. It's the price before it started to decline, right? It's the price before it started to decay. As soon as you drive it off the lot, it's going to be worth less, right? Because now it's used. What is the decay factor? 1 minus r written as a percent. 1 minus 15% is 0.85 or 85%. What value makes sense for the domain and the range of this function? So your domain, what do you think your domain is? Non-negative real numbers. You can't have negative time, right? You can't have any of the negative numbers. You can't have negative 5 years, negative 10 years. So your domain, instead of being all real numbers, it's only going to be the positive numbers because of the fact that it's time. Does that make sense? Yeah. Yeah. What about your range? Real numbers greater than what? Greater than 0 and less than what? 12,000. Your car's not going to be worth more when it's used. It's decaying. So if I was going to write this, it'd be greater than 0 and less than 12,000, right? Your range is greater than 0, less than 12,000. I guess technically less than or equal to 12,000, right? Predict the value of the car after 10 years. Well, what was our equation? So we had 12,000 times 0.85 to the years. So 0.85 to the 10th times 12,000. It should be worth approximately $2,362.50. In how many years was the value of the car 8,000? So this one's a logarithm, right? I'm going to divide by 12,000. And I'm going to do the logs on both sides. So log of 8,000 over 12,000 equals log of 0.85 to the x. That x is coming out front. Then I'm going to divide by log 0.85 on both sides. And that solves it, right? So 8,000 divided by 12,000 log divided by 0.85 log equals, I got 2.49 years. So they wrote about 2.5 years. About 2.5 years. Explain why exponential functions of this type are referred to as exponential decay functions. Because the value is going down. It's going down. We're yelling timber. All right, so the initial decreases or decays. The initial value decreases or decays with the passage of time or over time. Comparing exponential growth and exponential decay. So the graph shows the values of two different shares of stock over a period of 4 years since they were purchased. The values have been changing exponentially. Describe and compare the behaviors of the two stocks. The model for the graph representing stock A is an exponential what model? Stock A. Decay. The initial value is $16. And the decay factor is, what's the decay factor? 12 divided by 16, or 0.75. The model for the graph representing stock B is an exponential. B is an exponential growth. The initial value is $5. And the growth factor is 6 divided by 5, or 1.2. The value of stock A is going what over time? Down. The value of stock B is going up over time. The initial value of stock A is greater than the initial value of stock B. However, after about blank years, the value of stock A becomes less than the value of stock B. How many years? 2.5. What is the growth rate for the increasing function above? Explain your reasoning. So it was 20%. The growth factor is 1.2. So 1 plus R equals 1.2. R equals 0.2. What is the decay rate for the decreasing function above? So that one was 25%, right? So the decay factor was, the decay rate was 0.75. So 1 minus R equals 0.75. So R equals 0.25. right? If it's going down 75%, that means that the rate was 0.25. How did the values of the stocks compare initially and after 4 years? So initially, stock A was worth $11 more than stock B. After 4 years, stock B was worth just over $5 more per share than stock A. In how many years was the value of stock A about equal to the value of stock B? Explain your reasoning. When were they about equal? In 2.5 years, right? About 2.5 years. In 2.5 years, the value of both stocks was about $8 per share. In how many years was the value of stock A about twice the value of stock B? Explain your reasoning. When was stock A double stock B? That's like 6 and 12. Look, right here. That's 6 and 12 in 1 year. About 1 year. In 1 year, the value of stock B was $6 and A was, so B was $6, A was $12. Which is twice B, right? Make sense? All right, so let's go on to this practice problem. So complete the table for each function. So if I had number 1, and I wanted to know what is my initial amount, what do you guys think? What is my initial amount on number 1? What's my initial amount? 1,250. On number 2? On number 3. All right, so we're good on finding out the initial amount. How about the growth rate? 0.02, 0.5, and what? They combined it already, guys. So what is it supposed to be? 0.06. Okay. My growth factor. So if it's going up 2%, it's really 102%, right? 1.02, 1.5, 1.06, right? When you have to add them together. 1.06, 1.5, 1.02. Write an equation for the exponential growth function. Eva deposits $1,500 in an account that earns 4% interest each year. So 1,500 times 4%, 1.04 to the x, right? So that's going to be y equals 1,500 times 1.04, the time in years. Try number 5. Try and write that equation. You guys get it yet? Y equals 255,000 times 1.06 times the number of years. Brian invests $2,000. His investment grows at a rate of 16% each year. So Y equals $2,000 times 1.16 times the number of years. Sue is a coin collector. At the end of 2005, she bought a coin for $2.50, whose value has been growing 20% per year for 3 years. The value continued to grow at this rate until she sold the coin 4 years later. Write an exponential growth equation for the situation using the amount Sue paid as a value of at time 0. Try and write this equation real quick, guys. You guys get Y equals $2.50 times 1.2 to the T. All right, so now let's plug and chug. So anything to the 0 power is 1. 1 times 250 is 250. Let's plug in a 1. 1.2 times 2.5. I got 3. Plug in a 2. 1.2 squared times 2.5. 3.6. Plug in a 3. 1.2 to the third times 2.5. 4.32. And this is all money, right? 4, 1.2 to the fourth times 2.5. I got $5.18. How about a negative 1? If I plug in a negative 1, 1.2 to the 1 negative equals times 250, 2.08. 1.2 to the 2 negative equals times 2.5 and 1.45. Okay, graph. So I'm going to do negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. And then for this, I'm going to go 1, 2, 3, 4, 5, 6, 7. Right, negative 3, 1.45, negative 2, 1.74, negative 1, 2.08, 0, 2.5, 1 is 3, 2 is 3.6, 3 is 4.32, 4 is 5.18, what is the domain and the range for the situation? Domain. All real numbers from negative 3 to 4. Range. All real numbers from 1.45 to 5.18. Identify the y-intercept. It's the $2.50 that she paid for it. What is the value of the coin at the end of 2003? At the time she sold the coin, explain your reasoning. What's the value when she sold it? She bought it at 2005, right? Four years later. 2006, 2007, 2008, 2009. She sold it in 2009. What is the value of the coin at the end of 2003? 2004, 2003. $1.74. At the time Sue sold the coin, $5.18. Explain your reasoning. Right? So